And today, Esther will present mostly our master project, master thesis.
Yeah. So I did my master thesis at ASML, and this was the project about lithography, which I was also working on for the past month, and we'll be doing some experiments for that still in the coming 2 months or so. So then you also know what I'm doing now. So the title of the paper that we also submitted about this was embedding for generative modeling in inverse lithography. And first, a quick background on what is lithography actually. So what we do in ASML, we print chips. We make chip machines basically to produce chips that have a certain pattern. So that's done via light source that emits light, which is then condensed by a series of lenses, passed through a mask to produce a certain pattern, is focused again, and then is cast upon a wafer or photoresist. And what's happening in the wafer is that the light burns away part of the material that's on there, and then in that way it produces a pattern which can then be produced later into an actual chip. So that's the thing about lithography, and then the mask is basically a blueprint of the wafer. So what shines through the gaps in the mask also is projected onto the wafer. So what we would like to do is just get a desired target for on a chip, and then copy that target into the mask so that it's exactly the same. And then when light source falls through it, we have the actual wafer. However, the system is optically limited because we are working at very small dimensions. So we run into the diffraction limit, and this causes errors. And a solution that's typically used is to change the mask to account for these errors. So we do that by adding assist features, and you can see an example over here. So this is the actual wafer that you want to have on the chip, which is then also printed over here. And to make sure that that's printed, you need to add all these wobbly features, which basically help to focus the light. So to formally introduce that, we have some definitions. So our desired target phi, that is what we actually want to have on a chip. Our actual wafer target omega, so what is printed on the chip. The mask pattern and a forward model. And the wafer target is then given by putting a mask through the forward model, which models the lenses and the resist behavior. Now, it would be easy if we could just compute the inverse, but that's not possible. And therefore, the optimal mask is found typically by minimizing the cost function, which optimizes for the difference between the actual wave target and what we want to have. And that's the basis of inverse lithography. Now, there are some challenges. So I already mentioned there's no inverse function. Then second, the inverse mask optimization is very costly. So in terms of time, it can take like weeks to produce to compute the mask required to print a single chip. Maybe even more since a chip consists of multiple layers, and that all adds up. Then also typically images of desired wafer targets are used which are not scalable, which means that if we want to have high resolution, the image needs to be higher and the problem scales quadratically, which is not nice. And then also to come up with a solution to the big data sizes, typically we use patching, which means that we break the chip up into the separate patches. And when you compute the mask for like each of these patches, you then have to combine the masks. And, combining them over here introduces inconsistencies since there might be different solutions. So that's also a problem. And therefore, my research goal during the master thesis was to find a new approach to that, based on what they actually wanted. So they wanted a mask design with little room for errors. They wanted it to be possible to make changes to the chip design, so to have a bit more of a flexible setup, where if you change one feature, you don't have to recompute the entire chip, but you can just focus on that small area to recompute. And also it should be scalable, and that on a limited computational budget. So that's the introduction now for the methods. So I used, first of all, a deep learning model. And a typical model uses deterministic one-to-one mapping, which is not nice since I forgot to mention, but when you add the assist features, you can basically add them in multiple ways. So there are multiple masks which will produce the same wafer target. And that's a problem. And for that, we need to use a generative model so we can sample one of the possible options. So we moved on to generative modeling, and then the backbone of the model was a variational autoencoder where you need to sample one of the masks. And our goal for the optimization problem was to maximize the evidence of P5. So to maximize the likelihood that we indeed get our desired target. And to do that, we used sampling of one of the masks. Now for the primitives, we also wanted to model them in a sharp, smart way. And for that, we observed that every target design, so this example of target design, it consists of several basic shapes. We have rectangles and squares, and they're ordered in some way that has some pattern to it. And what we basically thought was we can combine, we can make a set of these basic shapes, we call them primitives, and combine a set of primitives into a feature. So here you have two features, you have, for example, this one, and then one on top of that, and they're both made of the same set of shapes, but different. And we formulated it mathematically using this formula where we did the convolution of the shape and the position coordinates of all the primitives. And in that way, we can describe our entire target. So the motivation to do that is, first of all, we can reduce inconsistencies from the patching, since the entire input will be more localized. So instead of having one image, we have a set of primitives which we try to project into a mask. So we can just change one primitive, for example, redo the mask sampling, and then get a new output instead of having to recompute the entire image. And also now the size scales with the number of primitives instead of with image size, which is much more favorable. And it offers a flexible setup. Then for the generative modeling, so the entire model we want as input we have pi, as output we have sine omega, so the mask and the wave targets, to reconstruct the targets. And then we also introduce the latent variable set, which is used to produce the wave target mask. So yeah, these are deterministic functions. So we sample actually set, then produce a mask and wave target from them. And we use variational inference by using the variational model of Q. Yeah.
This is conditional distribution. It's not like just a distribution. So phi is the point mass here, or like it's a second equation. Because you get two phi given z, you given phi.
I think by this point the target is given, right? So you can
So phi is the phi
is given.
First the input.
Okay, it's what I just thanks.
And we wrote alpha for that, and have rewritten it as follows. So there are several terms in here. We have the first term, which is the joint plausibility of the generated mask and wave projection. And this basically means that if you sample the latent variable and reconstruct the mask and wave target from them, they should be consistent with each other. So a predicted mask should correspond to the predicted wave target, otherwise it makes no sense. Then we also have the data fidelity term, which is basically if the reconstructed wave target will actually be the same as the input target. And then there's some stuff, the Gale convergence between the latent variables and also an entropy term, which is 0. And in terms of the model architecture, this looks like this. So we have the primitives, we put them into the encoder to go to the database. Then we add a normalizing flow to make a more complex distribution from that. We sample, and then we go to the decoder to produce both mask and wave function. And we translate through the objective function by the This is a mistake. This term is the second term is the reconstruction error between the input and what we actually get out of it. Then this first term is the error term on the like the joint plausibility of the mask and wave target. I will come back to that later. We have the latent term and then also an extra error term for the flow. And as I said, we want to score the joint occurrence of a mask and wave target, and we do that by training a separate model that learns this joint distribution. So we call that the error prediction model. So it takes its input in combination of the output for the mask and the output for the wave target, and based on that provides a classification and regression score on how well they belong to each other. And that's the score that we use during mask prediction. So some examples, here's a mismatch sample. So you see that the input does not correspond to the mask, the shapes are different. So this would give a low score. And here we have, for example, very blurry samples. They do belong to each other, the approximate shapes are there, but still it's not a nice mask. So this would also get a lower score. And we tested that model and showed that it was good actually at classification and also at regression. It was quite well predicting whether they belong to each other or not. So we use that in the main setup and then we can produce some results. So this is for our proposed model, and the benchmark is just a simple autoencoder, where this is the wave target. This is the mask predicted by the model. This is the output of the forward model where we predict the mask. So this is what's actually would be. And then we see that overall the results are quite good. Also for this model, we can predict reasonable masks. The shapes are all there. To score them, we use the mean absolute error between the input and output. And then we see that still the benchmark does reach higher accuracy. So the errors are lower, but we also see that computation time for the proposed model is much lower. So like we're talking seconds here, where the other was taking like 10 minutes at a time. And based on that, knowing that accuracy was not our only criterion, we can conclude that it's actually quite good. Then he also did some Bayesian studies with different setups. So I tried using images into our proposed model instead of primitives. And that works better. It's easier since we don't have the extra primitive setup, which is slightly more difficult. I also trying to deterministic setup, so basically trying to do a one-to-one mapping, which scores slightly worse, and also not using the error prediction model, so a naive loss term between the predicted mask and the input mask. That also scores worse, which is logical since the model might predict multiple output masks. You don't know which one, so it's not necessarily the same as the input mask. And using no error prediction model but a simple, for example, mean squared error loss does not account for that. And in all cases, we see that the results are consistent for both the mask and the wave target, which means that the decoders are trained well, but also the latent space is like basically well enough to predict both of them and to make sure that we have consistent results. I also tried to produce the spread in the mask domain. So this means that we test whether the model is able to actually predict separate masks or it just collapses to one output. And then we see that there's, for the proposed model, actually a lower spread in the mask domain, so that's not good. But then also low spread in wave target domain, which is good, since for each mask we have the same wave target. So that's ambiguous results. Then moving on to the conclusion, we had a few challenges. So the high computational cost, which we solved by using the deep learning model. We had the one-to-many task, which is on a conceptual level solved by using generative modeling plus error prediction model, but results aren't that accurate yet, so it could still be improved. We had the fact that the image data was not scalable, which is solved by the primitive setup. And we had the patching problems, and that's also reduced by the primitive setup, but should still be tested further. So overall, the study was a proof of concept. So I tried to test different ideas, and the models can still be optimized. One of the suggestions for further work was to use graph neural networks. The advantage for this is that you can view the primitives more as a vector, so it suits the structure of the data better. And I also need to diversify the dataset that I use, since the features were quite limited, and moving features close together or farther apart, or using more features in one image breaks the model quite easily, and that should be tested. And in a similar manner, if we make the training distribution more representative for the error prediction model, it should operate better, and that would improve the entire proposed model. Yeah, that's basically what I did.
Anyone have any
Can you go to slide 17, because I didn't really understand yet what this error prediction model does. Yeah, next. This, yes.
Yeah.
Can you explain again what again?
Okay.
What does it do? It takes.
So if you have,
It takes.
this is the variable.
Yeah.
Yes. So at the end, we output from that a mask and weight.
Yes.
Now we need to know whether these things correspond to each other. And basically we do that because we have no other way to store the predicted mask. You cannot just compare the predicted mask on the input mask, because they might not correspond to each other.
It's like a generative or a.
You get a setup.
It scores whether or not the mask and the wafer target correspond to each other.
Yeah. So whether the predicted mask is smooth.
So you passing it once again to the forward model and compute some
Yeah.
form of an error, right?
Yeah, I could use the forward model for that, but
Yes.
that's too expensive to do on training a model.
So how do you estimate it then?
Yeah, with a separate model.
Instead, we use the separate model to score whether the mask is suitable.
So that kind of approximation, the second model is approximation to the forward model.
And that's his first term.
Conceptual level, yeah, but not how it's implemented.
That's the first term, right?
Yeah, that's
So this P theta is your error prediction model. It takes both your transform Z in mask and in wafer target. Okay. So you embed your. You embed your desired target and then generate both a mask and a wafer target. Check whether or not they correspond to each other.
Okay, so this predictive model is not like so it's cheaper, like kind of on the conceptual level. I don't understand why it's cheaper. It's cheaper because forward model produced me a whole picture, but this just produced me a value. Are they close now? Are they far away? Something like that.
No, I think this F function is this 30-hour computational lithography thing.
no, that's the inverse computation. It's still that's for the optimization problem, but still for the forward model, it's like a physics model, which takes some time to.
So this F is not learned. It's given. This F in your this not graph. This is not learned.
Yeah,
This is given.
Yeah.
Yeah. Right. And that's the.
Yeah.
From our expense.
Yeah, and also F is taken equally producing it very this P data just produced me value. So I was like, it's why it's cheaper, right? It's my intuition is correct.
I don't know if you can compare it in that way, since there is not a deep learning model or.
Yeah, but you're saying I'm just.
Yeah, but still you take their two images as input, so you could say, okay, that's also expensive.
Yeah, but it's not a question like is it expensive? It's all relative terms, right? Because you said for training the model is very slow, and so you said, well, the data is faster, and I'm trying to understand why Petita can be learned very good, and so why computation of Petita is actually cheaper. When I'm putting there G size B and Q, so I'm assuming that what's written in this expectation is taken in samples, right? So you sample these Z's from latent space, you take a average of accuracy term, right? And you say this is faster than using the format model.
Okay, maybe some intuition behind this is that if I show you two of the, for example, the pictures you see over here, you can quite easily see with the eye whether they match or not. So you know, okay, this is the input shape. In the mask you still have those like big shapes and then the cyst features around it. And it's easy to interpret that this is a match. Right?
Yeah.
So if you just do like a basic subtraction of the two, you already have a good indication on whether the images match or not. And that's very easy for a model to learn. Whereas using an entire forward model that has to do the computations and like also through a system of lenses, basically, it's harder.
So it's kind of what you say, it's comparison between generator and verifier. It's easier to train the verifier.
Yeah.
Okay.
But if you have this, so you can put in a wafer target, and not just compute gradients with respect to the mask, and then put this loss to zero. If you learn basically a joint probability of wafer target, then so you set your wafer target to your desired target, and then just do backprop with respect to the input mask, and you'll get an input mask that.
Yeah, but the analytics model needs to be differential, right?
Yeah, but she learned it. She learned it with p-theta. She learned to correct to.
Yeah, but p-theta is itself a differential with respect to theta, but it does not mean that G psi t or G.
Forget about G. Just put it psi. It has to be differentiable with respect to psi.
No. Why?
In what I said. Just for my own
Esther,
understanding.
does it need to be differentiable with respect to psi?
Can you clarify what you mean? Like you mean you want to do like optimization by gradient descent?
Yeah, I want to optimize the input mask with gradient descent based on my wafer target. Because I want my wafer target to be the desired target, so that one's fixed. I have a trained model. So I just want to optimize this term with respect to the input I put in.
But if you make it differentiable to psi, will you still be able to predict multiple masks?
I don't think so. I think you'll just get MVP. You'll just get one mask.
So that's the problem.
I have a lithography question. At some point, you said, well, I have good results. I don't know the sign it is, but basically show the resulting image, this one, yes. And you said it's good, but I don't know anything about lithography. But when I see this F slide and omega, like the image seems very blurry to me. There's an issue, like for instance, you see that you don't see, for instance, the two dots at the end of the line.
Yeah, okay, so it's not exactly the same, so that is always a problem. But then that's true for both the benchmark and the forward model, so it's a bit inherent to using model to predict mask or wafer target. It's a more difficult task. Getting exactly this image is quite hard. And in real life, this wouldn't be good still. What's more, we prove that the model is able to learn the combination of parameters. So it's not using this as an input image, but just a set with a set of coordinates. It can still use like the approximate shape of the mask and also the assist models. So then we can maybe tweak it by if we make the input a bit more pronounced, like the quicker, for example, you also see that all output shapes will also get bigger and a bit closer to what the machine.
So basically, you're good compared to the benchmark, but not as good enough compared to the application.
They'll stay.
Obviously, it's a research. And are you allowed to display, because you said, well, I have this latent variable set, right? Can you explain a bit like what is it? Because for instance, you basically do this initialization. Can you explain a bit how this model looks like, or is something, I don't know,
Yeah.
the generative model? What is a normal distribution? My question is, how complex is this model? It's not.
So you mean over here?
Yes.
Yeah, so set is just a little variable, so we are able to produce both mass and wafer. So this is very simple. It's like just an autoencoded basic straight up a bunch of conclusion layers, no fancy tricks, and then the only thing we added to that to make it more complex is the normalizing, which is also quite easy. But yeah, that might also be a problem because I tested by using by different figures that then yeah, the output was messed up basically. And we also saw that probably this distribution sets of complexity.
Okay.
Another question, once again, how the set of primitives, this library of primitives, how it was made? It was made by humans.
I made it.
Okay. So this is kind of manual labor.
Well, I defined like some basic shapes. So I had the rectangle, the square, and then also a corner shape. And that's just like I used the same vectorized image setup that's used in industry. So the same data format basically, that you can vary the length of the height and width basically of each shape. And based on that, you have any feature you want.
Yeah, but it sounds sort of to me is strange. Because when computer vision just happened, people what they did, they prepared the primitive shapes, they match over the math over the limit. And after what was being figured out the convolutional neural network that can just learn this primitive. So do you think this part of primitives where you maybe I prefer like triangles, squares, corners, actually can be displayed by convolutional neural network, and then you can kind of train it end to end.
Yeah, I mean training. You mean training image to image?
Primitives as well. Like,
Yeah, training image. Yeah.
yeah.
So in a network, extract the primitives and then train the rest. I mean, you could do it, but the whole point of using the primitives is that it's more flexible. So now if I have an input image and I want to change a single primitive, I only have to put that single primitive through the encoder again, and then I can sample. I can just aggregate a new combination of primitives and sample from that. I don't have to recompute an entire to like encode an entire image, which is in practice really big.
Yeah.
And that makes it nicer.
That sounds about
It's just the computational cost of the image. So this is cheaper. And ASML seems to care about it.
no, I mean it's fine.
So it's not the best setup, obviously, but it's a more cheap setup.
Yeah, I'm just wondering because to me this was prepared by hand, and so it's the natural choice. Well, can we optimize the primitive so they give it better pipeline? So my naive suggestion was let's drop.
Okay. I think so, yeah, but another advantage of the primitives is that when you're a customer at ASML, we don't know what their input looks like. So if we can just give them a set of our primitives, let them build a target image from that, and then we know that their target image is within our defined sets. So that also is one of the benefits.
Yeah, I understand.
I have the last question. So this is your master project. Now you are doing a PhD. How does this integrate into your PhD project? What are you some next step?
So for this, my next steps will be more experiments to show where the model breaks and what works, basically. And then the original idea was that I would just continue with this project, try new models, try to come up with new solutions for things. That changed a bit, and I'm shifting to a different topic, which is metrology. And I can give a presentation about that, but not in a couple of months, since I have to learn a lot about it.
Okay, all right.
So I'm not entirely sure how much I will be doing with this anymore.
Okay.
Yeah, that's to be decided.
Yeah. And
Final thing before we go. No, you're not getting out that. Because we don't have a room this week. I'll do the developer of the Fortnite award here because we all know afterwards we're going to spend 3 full hours